My name's Zina Farouk, and I'm the application engineer for the geotechnical aspects of Oasys. I am a geotechnical engineer as well, and I have a number of years' experience of geotechnics with Arab. So today we're going to cover Frew, but we're going to focus on navigating around the program and showing aspects of the program and how it works. So for the presentation today, we're going to have two aspects of the presentation. One will be the PowerPoint presentation, where I inform you of the analysis methods of Frew. I help you understand the way it works. And I also demonstrate how it's used in industry through case studies. But the main bulk of the presentation today will actually be through a live demonstration. I'm going to run through two examples, one simple stability analysis, and one full soil structure interaction analysis for a construction sequence for a retaining wall. And I'm going to show you how easy it is to set up a Frew model and run it. So, for example, using the modeling wizard makes it much quicker to run. And also, there are a number of shortcuts and tips to enable very proficient modeling. So these should help you set up models much more quickly, and hopefully you can see how that is done. I'll also be summarizing simple checks. So, for example, when your analysis is complete, what should you be doing? What should you be looking at? How can you ensure that you're happy with your design, and just simple checks, really. Seeing that we're covering quite a lot in terms of the navigation of Frew and how to get around it and how to use it, I'm not able to cover some of the more advanced features in Frew. So other webinars firstly have tutorials in them on setting up models. There is also webinars covering the more advanced features of Frew and specialist features such as integral bridge analysis and the EC7 design methods. So starting off, well, we need to start with the analysis theory before jumping into the demonstration. So to start off with, what is Frew? Frew is an embedded retaining wall analysis over the complete construction sequence. It carries out stability checks using limit equilibrium methods for cantilever and propped walls. But using soil structural interaction analysis, it calculates earth and water pressures at every stage. It will calculate bending moments, deflections, and shear forces. It's suitable for sheet pile, secant, contiguous, or diaphragm walls. And the way you would adapt the type of wall would be by changing the stiffness of the wall, which is accessible through the gateway in Frew. How did Frew come about? Well, it's based on theory and research done some time back, based on the paper Numerical Analysis of Flexible Retaining Walls. However, the current version of Frew, which is Frew 19.1, is very, very different to what was initially proposed. So now, for example, not only is the actual program in itself and the way you go around the program different, but there are lots of extra features which were not initially there, and lots of extra theory is covered currently. So for the analysis theory, the way Frew works and the numerical representation is very important, and it is important you understand this. The wall itself is modeled as a series of elastic beam elements, and these beam elements are connected by a series of nodes, and the soil to each side of the wall is connected to the nodes using kind of spring system, and only horizontal forces are transmitted. And at these nodes, for example, prop forces can also be transmitted, and so on and so forth. At the bottom of the model, you have a rigid base, and the rigid base is often taken, for example, at rock level. You've also got vertical rigid boundaries, and these are set to some distance away. However, if you're doing something like a shaft analysis, you might want to take the line of axisymmetry and take a smaller rigid boundary in the vertical direction. The wall can be taken from the top of the problem, or you can actually start the wall lower down. So you can start the wall below the surface of ground level. So for the soil stiffnesses and calculating the soil stiffnesses, there are two methods which are available in Frew: the finite element flexibility model and the Mindlin flexibility model. And what happens is that these two models are used to calculate the response to the stiffness matrix. And it calculates how applied loads to the edge of the finite element mesh affect the stiffness of the soils, basically. So the method that you choose, either SAFE or Mindlin, are very similar, but more description is given in the user manual as to which of these methods should be used for different types of problem, and you should make yourself familiar with that. We're often asked about the theory in terms of how conservative is Frew, how practical is it? There are assumptions which are made in Frew. You simplify the likely effects of wall friction. You simplify the actions of structural support such that they basically act as a force on a node. And you do assume linear elastic soil stiffness. Having said that, a number of comparisons have been done, and they compare reasonably well with FE analysis, and they compare reasonably well with site readings. So Sirius C580 carries out a very thorough analysis using Frew and compares it. When I say compares it, I mean the bending moments and displacements and so on and so forth with a finite element analysis, and they compare very well. In terms of empirical analysis, there was a paper published by Rocco on the CTRL contract Ashford tunnels, which shows that the Frew predictions are very close to actual predictions on site, actual measurements on site. And there's also a case study available on our website, which covers the Hong Kong cutter cover tunnels and shows you how closely the Frew predictions match to site readings. So now I'm going to talk about the actual program and what you would do and how you would set up the program. So you have to think about the inputs before you actually start up the program. So what's your soil stratum? What are your soil strengths and stiffnesses? What are your soil properties in the short and long term? Where is the groundwater and what are the groundwater pressures? What is the wall stiffness in the short and long term? And this depends on your type of wall. How about the support stiffnesses and the supports themselves? Do you have props or anchors or berms or slabs? What type of stiffnesses are acting on them? And also, are there any surcharges acting either in front or behind the wall? And what are the applied loads on the wall? Once you've done this, you also need to plan the geometry. And when I say plan the geometry, I mean, for example, if you're planning a construction sequence, what are the levels of dig? Where are the prop positions? And also, are you doing an SLS or ULS analysis? Because you may need to vary your dig levels, for example, if you're doing an EC7 analysis. You also need to think about automatic node generation versus manual node generation. And what I mean about this, and I will demonstrate this much better when you go into the live demonstration, is that if you're automatically generating nodes, you don't need to think too much about soil levels and prop levels and various other things, because once you've inputted it into the program generates the nodes for you. However, you might decide, you might be a more proficient user, you might want to manually generate the nodes. Alternatively, you might be looking at an older Frew file. And if that's the case, you have to understand how nodes are compiled. So for example, you need to know that prop loads are applied at nodes, that soil switches between nodes, that you need to keep nodes approximately equally spaced. And if you go too far away from these rules, the actual analysis isn't as accurate as it could be, and it is often the case as well that, for example, if you put far too many nodes in, you might find that your analysis is very slow. So to get proficient results, you really need to understand a little bit about node generation if you're going to go into the manual node generation area. And one reason people do actually manually generate the nodes is because they may want a node in a very specific point, maybe because you're looking for a displacement or bending moment at that point. So just be aware that you should be aware of the rules as well for this. Other than that, passive softening can also be specified via the analysis data. So if you've got passive softening at any stages, be aware of that and make sure you specify it. As well as the inputs, there are features which help you run the Frew file. And so I've mentioned the model wizard. That what the model wizard does is it gives you something at the start. It sets up either your initial condition or your one stage for your stability analysis. It also has automatic node generation. And should you need to, there's manual node generation. There's limit equilibrium stability checks. So what happens is if you had a number of construction sequences, previously what people would have been doing would be to actually carry out a hand check, or alternatively go into another program and look at doing a limit equilibrium check for what they would think would be the worst case stage. But now what Frew does is it does the check for every single stage. So although you should be aware of what your worst case would probably be, it does do a check of every single stage, and it does find you the minimum toe level based on that. And as you can see here, this is just an example. You've got the toe depth for a number of stages, and the minimum toe depth here is 37.34, which is shown by this red line here. More advanced features of Frew 19.1 is the manual override, as I previously discussed, and a very useful feature which is used quite a lot, which is batch testing. What batch testing is that you may be designing a wall and you may think that your toe level, for example, would probably be 37.34, but you may be interested to see what would happen if your toe level was a little bit shorter or a little bit longer. Maybe, for example, you're doing a comparison with a ULS analysis, or maybe you just want to see, a slightly cheaper alternative. So instead of actually going back into Frew and creating more and more files, Frew allows you to actually create a number of files just from this one process of overriding your initial toe levels, specifying a range of levels, and creating multiple Frew files. So for those multiple Frew files, you can actually look at the performance of the retaining wall at different toe levels. So it's a very strong feature. So once you set up the model, you get very good outputs from Frew as well. There are graphical and tabular outputs available. You can export the tabular outputs to Excel. So should you want to do more advanced analysis, you can do so. You can also, for example, print out graphical outputs just for one particular stage. Or you could print out graphical outputs, say, for an envelope of results. What this means is that you may have 11 stages, but you want to know your worst case displacement. So for this kind of problem, the envelope of results would be very good because it tells you that your maximum displacement for all your stages is this much. So there are also a lot of opportunities with the outputs. I'm just going to touch upon the more advanced modeling methods. I'm effectively going to list them for you because they are covered in another webinar, which my colleague Nick will introduce to you at the end of this particular presentation. The kind of effects that can be modeled in Frew are, for example, you can accurately model the undrained to drain transition in Frew. And this is very good, for example, if you're looking at a long-term analysis. You can model props in Frew. Relaxation and creep can be modeled in Frew, and that's very important. You can model sloping ground, and you can also model berms. And details of this is given both in the manual and in the presentation, which is available on our website. And also thermal effects. So in the long term, you can actually model quite a lot of features within your retaining wall with Frew. I also wanted to touch upon EC7. Again, there is another presentation which covers this in a lot of detail, but Frew allows you to apply partial factors. Now you can apply partial factors to British standards, to Syria guides, but Eurocode 7 is very pertinent now, and Frew incorporates the factors for Eurocode 7 for a quick and easy design. What Eurocode 7 is the limit state design. It considers ultimate limit state analysis and the SLS analysis. But for Frew, you would really be using the partial factors to carry out your ultimate limit state analysis. The factors are applied to actions, material properties, and resistances. And you need to also, the designer also needs to think about, for example, characteristic geometries. So this is the section from section 9, which is relevant to embedded retaining walls. So the way EC7 works is that it asks you to factor a combination of actions, materials, and resistances. And you find your worst case and use that for your design or your ultimate limit state design. So this table just gives you an example of, for example, here the partial factors and effects of the partial factors on actions. So Frew has these pre-inputted, and you can just run an analysis and quickly click a button and get your outputs. Now, if you're not working in the UK, or you wanted a different national annex, for example, you can amend the factors, and it's saved in Frew as part of a library. So you can come back to that analysis again and again. So it's not very difficult to amend or change. So having covered a lot of the features of Frew and also the way it works in terms of inputs and outputs in the basic analysis, I'm just going to quickly summarize in terms of what Frew does. And that is that it analyzes the wall and ground throughout the excavation and construction stages and in the final condition. It checks horizontal equilibrium failure modes for fixed earth and free earth rotation as well. Okay, so having covered the analysis, I would like to demonstrate the way Frew works. And I'm going to start with a very simple problem, which is stability analysis only. And this is for a cantilever retaining wall. So if you have a look at the geometry here, we've got made ground shown in pink and sand and gravel overlying glacial till. There is a little bit of dig shown here. It's been dewatered, and there's also a surcharge of 10 kilonewton per meter squared. Okay, so if I go into Frew, I'm just going to start with a blank screen here for you. I'm going to start your analysis by pressing on the new button, and up pops the wizard. So as you can see, you've got a lot of options here for job numbers and titles and notes. And this is of particular relevance because this is what will be outputted when you print your tabular or graphical outputs. So it's very good for reports and checking. You've also got units, so you can change your units to whatever is useful. Now we have to set the problem itself. So at the top, we've got the top of the wall is at 50 meters OD. The base of the problem, where the rigid boundary is, or the top of rock, is 30 meters OD. I'm going to add the materials here. Okay, so we've got made ground, unit weight of 18, K0 of 0.5. We've got a stiffness here of 15,000. It's quite weak, so it's for the Young's modulus. We've got specified earth pressure coefficients of 0.29, 4.5, 1, and 1. Okay, so that's made ground inputted. We're going to add glacial till, unit weight 21, K0 of 1.5. We've got a constant stiffness with depth. We've got a stronger material here, Young's modulus of 45,000. C0, again, specified earth pressure coefficients of 0.3, 5, 1, and 1. Okay, and finally, I'm just going to add the sand and gravel. Okay, we've got a unit weight of 20, K0 of 1.5, Young's modulus here, reasonably strong, I think. 35,000 would do. We'll have a calculated earth pressure coefficient here. So I'll say 25, 27, delta over 5, 0.6, which is a standard. Okay, and no beta, and no. This is a drained analysis as well. So we're doing stability check only. So I've clicked on that area here. I'm going to go to next. Okay, now for either side of the problem, I need to enter the stratigraphy. So the made ground, the top of made ground is at 50 meters. The top of glacial till is at 46. There you go. And it's very important that you tab through here, because then it registers these things, otherwise it doesn't, and you'll have to go into the tabular output once you get out of the model wizard. 46.5 for the top of sand and gravel. There's a very small sand and gravel level there. And 46 meters for top glacial till. Finish. See, I didn't press the tab. So if I go into material layers here, you can see what I've done here. So I didn't tab through for this particular problem. I would like to say I did that intentionally. Glacial till in here. So as you can see, this is the material layers, and I've just clicked on the right section here. I put glacial till in, tab, and there you go. So this is my graphical input, as you can see. And don't worry about taking notes, because this will be available as a recording, and this is also available in the step-by-step tutorial manual, so you can go ahead and do it yourself as well. So we need to enter water levels. So I'm going to click on this water icon here. I'm going to right click here, and I've got 48 meters OD. I'm just going to type it into the table. If you look to your top right hand corner, you'll see there's a section here that says level. Okay, so what I'm going to do is I'm going to try and go to the correct level, which is 45 meters, 45, and click. And you can see then I don't need to amend the level here, and I can just click on, and I can have my dewatered level at 45 meters. The reason that this is useful is because if you are doing a more advanced analysis, it's quite nice to also be able to just click and do things, and sometimes you can do it quite quickly as well. Okay, so I've inputted the water, I've inputted the stratigraphy, and I'm going to check the material properties, which are looking absolutely fine for this particular type of problem. I'm also going to put my surcharges in. So through the gateway, I've clicked on surcharges. You can also access this through the surcharge icon, which I'm showing here. So when you go into the table input in Frew, you'll notice that there are these grey boxes at the top. Now these boxes are the defaults. So if I tab on a default, so say for example I'm on side here, I'm in this box in row 1. If I press tab, the default is taken automatically. So this just makes things much quicker. So for example, if I know every time my side is going to be left, I can just tab through it instead of typing left or going and clicking on left, for example. So the surcharge is the 50 meters OD. I'm going to tab through UDL. The pressure is 10, and I'm going to tab the partial factor of 1. So as you can see, it can be quite quick if you set your defaults accordingly. Okay, so I'll check the graphical input. Everything's looking good. I'm going to click here on the stability check. So if you can see, there's an icon here that says stability check. Okay, this is also available through the analysis at the top of the program. So stability check. Okay, I run the stability check, and at the bottom it's given me the toe depth, which is 43.4 meters OD. Okay, and you can also have a look at this through the graphical input. So there's stability check graphical input. I click on it, and there you go. You have the toe depth. You also have the shear and moment and actual pressure on the wall based on the limit equilibrium analysis. Now, for Frew, there are two very useful features. One is the exporting of tabular outputs. So you can actually export, so go through to File and Export, and you can save, for example, a tabular output as a CSV. And with the CSV, it means it's an Excel file, and then you can, do some more further analysis. And for either the tabular or graphical outputs, you can actually print. So as you can see, we've got, the company icon up here. We've got information from myself here, and you can also put your notes in here if you wish to do so. It is important to note that for a lot of you who are working in all sorts of different companies, you can actually input your own company info. So this is very good for reports, for example. You can also change the page setup and the way things appear, for example, on the program. I should also always mention that with any kind of analysis, it's important to save regularly. So that's covered the cantilever retaining wall. So just to summarize, I've introduced you to the input wizard. You've had a little bit of a look at the graphical input and how to click on things and input them in. We've got the tabular input as well, so input surcharges as a tabular input. I've mentioned exporting tabular inputs. I've shown you the graphical output of the limit equilibrium analysis, and I've mentioned the printing preferences and how you access it. So now for the more involved demonstration. This is a propped retaining wall, and for this retaining wall, we're going to cover a number of construction sequences, and we're going to carry out a stability and soil structure interaction analysis. So hopefully, this demonstration will help you appreciate the difference between the two types of analysis and why the two analyses have been used in conjunction as well. So for this particular problem, we start off with made ground overlying glacial till in the initial condition. We've installed the wall, dewatered and excavated. We've got a surcharge there as well. We've got the anchor installation. And then we've locked the anchor and excavated. So when we lock the anchor, we change the anchor property. So this is why the strut here is shown as strut 2 instead of strut 1. Then we have our final condition. So this is where we put the ground level slab and the basement slab in there. And we've got the sand. We've also got, again, the surcharge as it was before. Just to note, before I go into the demonstration, I just wanted to mention one or two things about the preferences and defaults. I did mention in the last demonstration that these grey boxes here are the defaults. And if you tab past it, you can fill the cell without having to write too much in. So that can be quite quick. Also, another table tip is if you want to copy from the cell above, you type in equals. If you want to copy the whole line, then you type in equal. So I will demonstrate this when we actually go in to Frew. Also, if you've got a very complex table, you can use Control-G to type the line that you would like to go to, and also right-clicking. Right-clicking brings up a whole list of options. Should you want to modify, for example, certain values, say you wanted to factor your phi values, all of them, you could do so by right-clicking and going to modify. Okay, so I'm going to go now into Frew and set up a new model. So there you go. I'm just going to click on new. I'm going to skip all that. We've got the top of this problem at 30 meters OD and the level of rock, the top of rock at 10 meters OD. Again, I'm going to add the materials. The reason I'm adding it and not copying and pasting from the previous problem, even though it's exactly the same, and you could do so should you wish to, is that this way I have, once I have my materials, I can set up my stratigraphy and start off with a problem as opposed to nothing. 18. Okay, so we've got 15,000 for the Young's modulus. It's a drained analysis, so no C0. I'm going to specify our K values, so 0.29, 4.5, 1. For soil structure interaction analysis, the KR value is important, and it isn't inputted here. So this is for glacial till, and I'm inputting this now. So what you need to do is once you've run the wizard, you would need to go into the gateway. Sorry, it's 45,000. You would need to go into the gateway and change your KR values to your design values. 1 and 1. Okay. I think that's enough. We'll skip scanning. Okay, right. So we'll put May ground and glacial till in there. We're running a stage construction. We've got automatic node generation. And also we're going to obtain the wall toe levels from stability check. So I'm just demonstrating the simpler features today. And should you be interested in anything else, there are tutorials available on our website. Okay, so I'm going to use the safe method for analyzing and for calculating the stiffness of the soils. So the wall soil interface with the safe method for this would be fixed. And if you want to understand how this works, this is connected to the safe method. You should check it in the user manual. In terms of boundary distances, I've just set a reasonably large distance here. But say, for example, you're running a shaft analysis, you would be running an axisymmetric analysis. So you might want to make this the distance to the line of symmetry. We're having generated Young's moduluses because they're much simpler, and Frew is able to redistribute pressures, so it gives you quite an accurate analysis. Okay, so for this problem, we start off with Mayground at 30 meters and Glacial Till at 24 meters. And again, don't forget to tab through. And again, Mayground at 30 meters and Glacial Till at 24 meters. Tab. Okay, so this is my initial condition. And for the initial condition, I need to firstly amend the material properties as I had previously mentioned. So I've gone to the gateway here and clicked on material properties under the global section. And I've got KR values of 0.5 and 0.3. So I'm just going to put that in there. Okay, so I need to also have a look at my graphical input. I access the graphical input through this icon here, which says soil zones. Okay, and I need to input my water levels. So I'm going to click on the water icon shown here. I'm going to click on either side, and water is at 28.5 meters in the first instance. Okay, 28.5. Okay, so this is our initial condition, but we're running through a number of construction sequences, so I am going to add a stage. For the first stage, it's install, dewater, and excavate. For simplicity, I've done everything in one, but often you would separate some of these stages out. So if I go again to the soil zones, for this particular stage, I need to excavate. So I'm going to go to the dig and fill button. I'm going to left click, and my dig level is 27.6. Okay, I am also going to dewater. I'm going to left click and dewater to 24 meters OD. And I am going to add stiffness because the wall has been installed, so it needs some level of stiffness. I'm going to put this wall at the top ground level, but it can be below that. And the actual stiffness value depends on the type of wall you have. Okay, so contiguous, sheet piled, whatever it is, that would impact on your actual stiffness. Okay, so that's stage one, done. Now I'm going to go on to the installing of the anchor and locking. Okay, so anchor installation. Okay, and add another stage, lock, anchor, and excavate. So as you can see, I'm following the planned geometry that I had specified in the PowerPoint presentation. So for the lock, anchor, and excavate, I'm going to go in here. And I'm going to have to excavate. So I'm going to go to the dig and fill icon. So that's up here. I'm going to right click and I'm going to go to 23.8 meters. Okay, so as you can see, stage 3 down to 23.8 meters. Okay, so now, nearly finished, we're going on to our final condition. Okay, so final condition. Okay, so this is final condition. As you can see, you can, just of interest, you can use the stage 3 to access information about any particular stage. So, for example, if I'm in anchor installation here and I wanted to find out the water level at that particular stage, I could do so. I could zoom into there and it'll give me water data for that particular stage. So you can use the stage tree to actually navigate around your problem as well. But we're going into the final condition now. And as you can see, up we go. So now we need to put in our surcharges and our struts. So I'm going to start with surcharge. Here you go. So surcharge comes in at, say, stage 1. Okay. And I'm just going to demonstrate to you how you copy and paste from different Frew files. And the process of copying and pasting from different Frew files is the same as copying and pasting from Excel. So you can actually also pre-plan problems, for example, and put things in Excel and then paste it in. So I'm going to copy here. Copy these surcharges and this data about the surcharge, and I'm going to paste in here. And as you can see, it's copied right through very simply and very easily. Now for the surcharge feature, this isn't necessary. This isn't necessary. It was just a little bit to show you how it's done. But during a lot of large projects, what I have done is I have made, for example, a materials table, and in Excel I have saved the material properties for a number of standard materials. And then every time I set up a new Frew file, I just copy and paste it in instead of having to type it in every time. So these shortcuts are useful, especially when you're working on bigger files. So we've inputted the surcharges. We also need to input the struts. Okay, so we'll start with the anchors. First, there's the anchor installation. So the anchor is installed in stage 3. It's put at 28 meters OD. There's a pre-stress of 200 kilonewton meters. There's a stiffness of 0. It's at an angle of 40 degrees, and there's a lever arm as well. Now, the next stage is where we lock the anchor. So this is where we're locking the anchor. I'm using the equals here. So if you look, I've just typed in equals, because instead of typing in 28, if I tab through at the equals, I'm getting the same level and the same pre-stress. But now I need to type in the stiffness because the anchor's been locked, and the same angle, again using equals, and the same lever arm. Okay, so now for the different levels or the different slabs, that comes in the final condition. So that's at stage 4. The ground floor slab is at 30 meters OD, so it's at the top. There's no pre-stress, but there is a significant stiffness. Now the basement slab actually has the same properties as the ground floor slab, apart from the actual level. So what I've done is, as you can see, I've typed in equals twice in cell A4. And if I tab that, I get exactly the same properties for everything. So now I just need to change the level, because we're going to say that the basement slab for this example is going to go in at 24 meters OD. Okay. So now we have all our struts. Everything's been done. If I wanted to look through my problem, I can use these icons next and previous to navigate. So I'm starting. I've clicked on the graphical input. I'm starting at the initial condition. If I click on next, install dewater and excavate, anchor installation, lock anchor and excavate, final condition. Great. Okay, so now I go into stability check. So there's the stability check icon. I'm going to click off this so that I can have a look at all the toe levels which are generated. So as you can see, we have a number of toe levels here. The lowest toe depth is 20.57 meters. Okay, and now I'm going to click on this icon here with a number of dots in it to generate the nodes. And what this shows is coincident soil node and fixed node at 24 meters, stopping node generation. I actually did do this intentionally, and the reason that this was done is because I wanted you to understand the way nodes are used in Frew, because this will change the way, for example, you plan your geometry. So what this is saying here is that we have a fixed node at 24 meters, which means we have the basement slab, if you remember, was acting at 24 meters. OD, and we put it in 24 meters OD. But a coincident soil node is also at 24 meters, and what this means is that there is a stratigraphy boundary, a soil boundary at 24 meters OD. So if you remember in the presentation, I mentioned that the boundaries act between nodes and that struts act at a node. So it's impossible for you to have both at the same value. So it says that the nodes can't be generated, and this does impact on how you actually plan your model. So what I will be now doing is looking at the struct properties and cancel the analysis. And actually, we'll say, okay, the basement is acting at around 24.7 meters. So the basement level is 24.7 meters. I'm going to run my stability check the outputs to see toe level. If I wanted, I could also look at the graphical output. Okay. And again, I'm going to generate the nodes. Of interest here might be the specification section. So for example, if here you suddenly decided you wanted to do a manual override or a stability check only, you could decide to do so by double clicking on specification. And again, as I mentioned with batch testing, if you wanted a range a range of toe levels, a number of files to be created, you could do that as well. Okay. I've also set here the maximum number of nodes to generate is 100, because if you generate far too many nodes, what often happens is the file can be quite bulky and take a long time to analyze. But you could change this if you've got a rather complicated file. Okay, so we're ready for the analysis. I didn't generate the nodes. Here you go. So I've run the stability check. I'm going to generate the nodes. And hey presto, because we don't have coincident nodes and solve boundaries, as you can see, we've generated the nodes here. It's shown here on this graphical section here, and the actual value of the nodes is shown in the table that I've just minimized. We're ready for the soil structure interaction analysis because we now have our nodes. And we've got our tabular outputs. So again, this can be exported if it's necessary. We can also print our tabular outputs. Okay. And very importantly, we've also got our graphical outputs. So I'm just going to click on full graphical output here. Close this. And here you go, we've got our graphical output. So I'm going to start at 0, the initial condition. This is just showing the pressure here in terms of your passive limit, which is the red line, and your active limit, which is the blue line. Okay, so we've got our initial condition, install, dewater, and excavate. So as you can see here, we've got the installation of the wall. We've taken the water down. As you can see, there are a change in pressures accordingly. We're installing the anchor here. So for the anchor installation, you've got the value of the force on the anchor, which is coming out. Locking the anchor and excavating. Now, this particular stage I want to focus on a little bit, and this is to do with checking of Frew files. So as you can see, we've got the actual pressure here, and the actual pressure is going beyond the active limit. So you would expect that the bending moment would be high due to this, and this is a good little check just within Frew. And as you can see, you've got a transfer of bending moments where you've got the anchor there, and you've also got a high bending moment where you've got the actual pressure going over the active limit. So that is as you would expect, and the program is running and as you would expect, and on top of that, the analysis seems to be in line with what it should be. You will also notice here that the pressure here is at passive limit. So if this is an SLS analysis, you might be thinking, maybe that's not great because you're going to get quite a large deflection, which you are getting here. So we've got a larger deflection because we've got our pressure coming at passive limit. And so the designer might look at this and think, maybe I could do with making the toe a little bit longer, maybe looking at putting a berm in here, for example, changing the level of the anchor to compensate accordingly. So these are, having looked at the outputs and understanding the way your retaining wall behaves, you can better understand what to do at different construction stages. So Frew allows you to do that. It gives you the power to understand better what's going on with your retaining wall. So if I do look at the final condition, you can see things getting a little bit better. So the bending moment is a little bit more realistic, and as you can see, we're getting slightly better results, so it's of less concern. But then what might happen is I might say, okay, that's my serviceability limit state analysis. What if I do a ULS analysis? What if I decide to put partial factors in? So maybe I wanted to factor here according to EC7 or Series C580 or BS 8002, or maybe I want to input my own factors. If you do that, then you might find that this would give you more worrying results, for example. So it's important that you understand what's happening, and then you factor accordingly, and you plan your design. And this webinar is really asking you to, or trying to help you think a little bit more about the way you design things, because Frew is a very good tool, but it's very important that you also understand the way the analysis works. Okay, so that's pretty much it for the live demonstration. And just to summarize, for the prop wall demonstration, we've covered the input wizard for the soil structure interaction analysis. I've covered a little bit more detail about graphical input using the staged icon to get the staged construction. Tabular inputs, I mentioned copying and pasting from Excel. I've also shown you how to use some shortcuts, the equals, and for example, using defaults. Minimum toe depth calculation, how powerful that can be, and how that makes your analysis much quicker. Again, automatic node generation. As you can see, there are some things that you would have to worry about with manual node generation. Automatic node generation makes it that much easier. Graphical outputs, the power of looking at different stages and how you can glean information from your graphical output, and how important it is to check your graphical outputs and understand what's going on, and then alter your design accordingly if it's necessary. Okay, so hopefully now you'll be able to understand a little bit more about Frew. You'll be able to navigate Frew and also understand the different analysis methods. So I thought it would be nice for you all to have a look at how Frew could be used for much more advanced analysis. There are a number of case studies available on our website, so the link is shown here. But I'm going to go through one case study which is being done currently in Arup in Hong Kong. It's a very deep basement design. It's the redevelopment of the North Point estate. So if we go into the plan here, you can see that the development is shown by this red line here. It's very close to an existing seawall, and it's very close to major utilities. It's also next to a pier and a port, so the material and the stratigraphy is probably not going to be great. So if we look at the detailed design, a 1.5 thick diaphragm wall is proposed at the boundary of the development with a maximum excavation depth, a significant depth of 13.5 meters. So there are a number of geotechnical constraints that the engineers had to consider. As I mentioned, there are poor ground conditions, so it's underlain by 10 meter thick reclamation fill, followed by 5 meter thick marine deposit, so a very low SPT and small shear strengths. There are also very stringent movement controls, one from the government who has imposed a very stringent ground movement criteria. So it allows 25 mil of movement to cater for all activities during and before construction. And also the site is encompassed by many movement sensitive structures. So if you remember from the plan, if I just go back into the plan, you can have a look and see we've got the existing seawall here, and we've got the culvert, and we've got the utilities. Okay, so for the tender design, it was proposed that you've got a diaphragm wall, which is 1.5 thick, reinforced concrete, and it will be supported by 5 layers of struts and 3 layers of permanent floor slabs. So Frew version 19.0 was used because this is the program which is accepted by the Hong Kong BD. The design of the diaphragm wall includes the modelling of the excavation sequence itself and determination of lateral deflections, moments and shear of the diaphragm wall. And the temporary and permanent conditions were analysed. So I'm just going to go through into the Frew file itself so that you can glean the actual analysis. So if I go right to the start, as you can see, we've got at stage 0, we've installed the wall, and as we excavate down, they put a number of props in. So you've got quite weak material here as well. So that's why you're getting the high deflections and bending moments. There you go. And in the long term, when installing here the walls and slabs. Okay. So this just gives you an idea of a more complex analysis. As you can see, a lot of different things have been done here in Frew. But a very complex analysis is possible, and using things like the graphical input, for example, it's reasonably easy to set up as well. Okay. So I'm just going to summarize what we've covered in the presentation. Our initial objective was to cover the analysis method in case studies. So hopefully you now understand how the Frew analysis works, the difference between limit equilibrium and soil structure interaction analysis, and what the case studies are used for. And the bulk of this presentation actually focused on navigating the program and giving you a demonstration of how it works and how powerful it is. So we carried out a stability and a full soil structure and interaction analysis, and we used the modeling wizard to set up a very quick analysis. We used shortcuts and tips to enable proficient modeling, and as you can see, the shortcuts and tips enable me to set up quite a complex construction sequence very quickly and get meaningful results out. We ran simple checks using graphical outputs. And so hopefully now you're able to navigate through, you're able to better understand how the analysis works, and you're able to now examine through and look into more detailed analysis.